observations of gravitational waves, these binary in spirals of black holes, we already are learning new astrophysics. And I show that not because it's profound necessarily, but because having a different way to look at the sky, to look at the universe, gives you new information. On the left here, I indicate that we learned some just basic things, that binary black holes exist. Secondly, that they merge within the lifetime of our universe, or we wouldn't have detected them. And secondly, lastly, that they're very heavy. That was a big surprise, that they can be maybe 20 times or 30 times or more than the mass of our sun. And the reason it was unexpected is that we think these come from the gravitational collapse, supernova, of a very heavy star. And stars can't be very heavy very easily because they basically are unstable with radiation hitting them from the outside. So, but they do exist, so now that has to be explained. On the right, you see mergers shown kind of graphically in different masses and so forth. That is just to illustrate that we're starting to detect enough of them that we can start to see distributions, for example, of the masses, of their spins, of all their characteristics. And that will be eventually the way we'll determine how they originated. And there are different ideas, again, for how they originate. The next slide, now what I'm talking about is what I want to spend the rest of the lecture on. And that is that we have instituted and believed from the beginning that a real important goal, as I said at the very beginning of the lecture, is to combine our observations with those that can be found electromagnetically. To do that, we have to be able to alert astronomers and astronomical instruments that we see something and tell where it is so they know where to look. And we basically have, I won't go through it in detail, we've instituted the ability to very quickly recognize pretty accurately that we see a gravitational wave. Maybe sometimes we make mistakes, but not too often. And also to tell where it is by seeing it in several different gravitational wave detectors. And then we can alert astronomers and they can point their instruments at that place in the sky. That's the idea. And then we spend hours or weeks, on the bottom I show that, actually calculating what we actually saw. So at the beginning, we just want to alert astronomers so we get information both astronomically and in gravitational waves. We couldn't point very well with just LIGO. This is a picture of how well we could point in some of those events that I showed you. Eventually, a third detector, just like triangulation when you work in a sailboat, for example, tells you more accurately. You can see in this picture here, this is the location where an event was seen, became known to 60 square degrees instead of 1,000 square degrees, which we had seen earlier, when we added information from a detector which became available in 2018 in Italy called Virgo. And so that gives us the ability to point. That was just in time to actually see for the first time where it might matter. All the previous events, the ones in black holes, there is nothing in the literature, no electromagnetic instrument believed they saw anything that we saw. So that's to be expected. A black hole doesn't emit anything. So nothing was seen. But I showed one event earlier that was in the apparatus a long time. And that one is shown here. And we did see where I write GW170817, where it was in the sky quite accurately with 31 square degrees of accuracy. It was 40 megaparsecs away, which is not so far. And we alerted the astronomical community. And within 2 seconds of the time we saw something, high energy photons were seen in the Fermi satellite. And that's shown in this picture here, where they saw them. That's their dark picture, how accurately they saw it. It overlapped our picture. And then with that confidence, other astronomical instruments in the world joined in and looked in different frequencies. And that included the visible radio waves, neutrinos, gamma rays, and so forth. And a big amount of information was obtained. First, if you look at the timeline, was ours, what we saw. We identified it as a merger not of two black holes, but of two neutron stars. Shortly after 1.7 seconds, these high energy gamma rays were seen. And then after 5 hours, other radiation was seen. After 10 hours, ultraviolet. After days, X-rays. After days after that, the longer wavelength radio waves. Using all that information, we were then able to fit it to a picture of what happens when these neutron stars merge. It's a picture that in the literature is called a kilonova. And I won't explain that. That's the nuclear physics of this coming together and the amount of energy that gets released. After you look at all the different wavelengths, the picture is very consistent with this model. This is just the data. The different colors are the different wavelengths, and as a function of time. So eventually, this is the amount of radiation coming and going when it was emitted. And all of this together fit this model of the electromagnetic spectrum. That's interesting because one problem that we've had as physicists is explaining, just an example of what you can learn, but is explaining how it is that the very heavy elements got into the earth. How is it that we can dig in the earth and find gold or platinum? Our picture of how the earth was formed is that most of the universe is made out of hydrogen and helium. The heavier elements that are there are mostly thought to be from the fusion process in the actual supernova or the collapse of a star when it finishes its lifetime. But fusion only works for elements up to about iron. It starts with fusing of hydrogen, deuterium, lithium, oxygen, and heavier, but only up to iron. So elements that are heavier than iron are hard to explain by that process. If instead you ask me how it is that we know all these elements at the top of the scale, they're done in a laboratory, and we do it by bombarding neutrons on other elements and then making yet a heavier one, detecting it, giving it a name, and putting it in the picture. But it doesn't mean that they would exist in nature. However, in the phenomenon of the neutron star merger, there's nuclear physics that goes on that can make heavy elements. It's different than the one seen before. And in fact, if you do the calculation, using this picture that I drew of the merger of neutron stars fitting this kilonova, the amount of gold that it made, for example, is 100 Earth masses of gold just in the collision that we observed. So in the past, there were earlier neutron star mergers that made the gold, platinum, and so forth, which we find in the Earth. So that's kind of an interesting new thing. We're getting better and better. And so the ability to use gravitational waves to study both gravitational waves, to work with electromagnetic waves, is only going to get better. We're limited by the instruments, not by nature. So this picture where I show O1, O2, O3A, O3B, on the vertical scale is the number of observed events. And you can see that they're climbing rapidly. We're now up to about 67 observed events of mergers that have given us signals. By next year, we will have improved yet more the apparatus that we have, and we'll start seeing events at about one a day. And in the future, we can do better yet, because as I say, we're limited by the instrument, not by nature itself. So what we're doing right at the moment in LIGO is we're looking at what we call exceptional events. Among those 70 events, what do we see that doesn't fit the normal pictures? And there's a couple phenomena, and I'll just mention them because we're getting near the end of the lecture. First, we know neutron stars are similar to the mass of our sun, about 1.5 times the mass of our sun, and can't be much heavier than that. Black holes can't be much lighter than about 3 times the mass of our sun, because if they're lighter than that, they can't be a black hole. They can't have enough gravity to basically make themselves a black hole. But we see events that are in between. So what are they? That's for us to find out and study now. And that's the first problem. Second, we see events that are too heavy. This is a picture of an exceptional event, which we only announced a month ago, which is 150 times the mass of our sun, probably a black hole merger, but we don't know that. You'll notice the signal looks different, and that's because what I show in the bottom in this picture here is the original signal that we detected and interpreted. Now I get a signal that looks different than that, but it's only the very final merger, so it looks like a lot like the last piece. We don't know that it's a black hole merger. It's so heavy that it doesn't fit the pictures we would have. It's what we call an intermediate mass black hole. There's supermassive black holes that are at the center of galaxies, but this is an intermediate mass black hole. And so these events, which we now call exceptional, this one very heavy, ones that are somehow between neutron stars and black holes, are what we're concentrating on at the moment. There's other phenomena that'll give gravitational waves, supernova, looking at spinning pulsars in our galaxy, or even signals from the early universe. And those will be done in the future. We know how to make the detectors better. This is just a picture of a design in Europe to make what they call the Einstein telescope. Instead of being 4 kilometers, it's 10 kilometers. And it's cryogenic, it's deep underground. It has arms that are longer. It's shaped like a triangle. And it's at least 10 times more sensitive than we'll finally achieve in LIGO. This shows the sensitivity. We're presently on this top curve. It'll be improved over the coming years to the curves in the middle. And then when we make a detector like is shown there, we actually can go yet further. And this is a log scale. So we get further down in sensitivity. That enables us to look further out in the universe. When we look out far enough in the universe, we start seeing early times or the ability to do cosmology with gravitational waves. So the future of the field is really, really very bright. First, we want to do what's done in astronomy, cover the different wavelengths. LIGO, as I showed, covers the wavelengths of the audio band. That's from 1 hertz to 10,000 hertz. At lower frequencies, we will soon have a probe sent in space called LISA that'll look for binaries and other objects at lower frequencies, 10 to the -1 to 10 to the -4 hertz. And at even lower frequencies, there's a scheme that's being put together and tested, but not quite accurate enough to do pulsar timing, do the timing of signals that come from pulsars, which would be distorted by the presence of a gravitational wave. Once we can cover all the frequency bands, then we'll be very much like optical astronomy and being able to study the universe in a really new way. In space, this is just a picture of what'll be done, a triangular object, 2.5 kilometer arms. This is the picture just of a pulsar timing array, which is being implemented now, and we'll look at even lower frequency. And eventually, we hope to see gravitational waves that even come from very, very early times. That'll be very valuable because we all care how the universe began. What was the Big Bang? What happened after that? How do we happen to have a matter-dominated universe? Presently, everything we know comes from photons, but they were absorbed before a few 100,000 years after the Big Bang. We can, in principle, go earlier with neutrinos to 1 second, and with gravitational waves to a fraction of a second after the Big Bang. So if we really want to understand what the Big Bang was all about, we can look forward to first neutrinos and then gravitational waves. With that, gives you at least a glimpse at some of the different directions that we will go. And we've seen the birth of a new kind of astronomy. Thank you.
Thank you so much. Barry?
Yeah.
We don't have questions.
From the live chat, we don't have any questions to you, but we have a small video question, and now you'll see this question.
Здравствуйте, я Федор Коршиков, обучающийся лицею Сириус.
Hello.
У меня есть вопрос по теме исследования Вселенной с помощью гравитационных волн. Можно ли эту информацию выразить графически?
Can we express this information in a graphic form? I mean, information we obtain by studying gravitation waves.
I don't see it. Am I supposed to see something on my screen? Because I didn't see anything.
Но я ничего не увидел на самом деле, говорит оратор.
Попробуйте еще раз ему перевести, пожалуйста.
Barry, we obtain information by studying, running research in gravitation and gravitation waves. Can we visualize this information graphically?
Yeah, well, just what you mean, like we do for electromagnetic waves, we see pictures of objects. We do the same thing. We do the same thing.
Электромагнитных волн мы изображаем объекты, мы их изображаем, но вот также графически в том числе, также и здесь тоже.
Yeah, so we do the same thing. We have a visualization of what
Итак, у нас есть способы визуализации.
Of two black holes going around each other and how they would merge together.
Процесса вращения вокруг одного центра масс двух черных дыр. Вот.
I don't have one of those movies with me, but you can watch a movie, for example, of two black holes colliding through calculating the trajectories using general relativity, and then showing an image of what we would see in our detectors.
Thank you so much. That's all for questions.
Okay.
And
We're done.
We're done. Yes.
Okay. Sorry for the technical difficulties.
No, don't worry. We have difficult technical difficulties too, but
yeah,
everything is okay.
Would have been much better if I were in Moscow, but unfortunately it wasn't possible.
Next time.
Would have been more fun too. So anyway, thank you for all the help.
Thank you.
Okay. Bye-bye.
Bye-bye.